Hello, everyone. My name is David Pugh. I'm a staff scientist at the CALS Visualization Core Lab. And today I'm going to talk to you about how to get started with Scikit-Learn for your next data science project on Ibex. So to help new users get started with their Scikit-Learn projects on Ibex, I have created this Scikit-Learn data science project template on GitHub on the CALS Viz Lab GitHub page. I'll put the link in the comments section of the video when this goes up on YouTube. This template project you can use by just clicking this, use this template button. And this will allow you to create a GitHub repository under your own user based on the current snapshot of this project template. So I'll just call this my awesome Scikit-Learn project. And materials for my next Scikit-Learn based data science project. And you can make it either public or private. It's up to you. You don't need to include all branches, just include the main or the master branch from the CALS Viz Lab Scikit-Learn data science project. And so we create the project from the template. Okay, now that this is done, we're ready to get this code onto Ibex. So we can clone this repository. And if you go over here, I've already logged into Ibex to the iLogin nodes. And I am, let's see, I'll cd to make sure I'm in my home directory. Okay, and now I actually want to create my, my projects on Scratch. So I'm kind of pretending I'm creating a brand new project. Oh, I've got this wrong. So Scratch. Ibex training. Okay, so I'm going to pretend that I'm making kind of a new project directory from this this repo. So I'm going to git clone the repo. Okay, and now I'm ready to go. So I can change into my awesome data science project, and then you can see here that I have copies of all the files from the repo that I just cloned. Right, so what I want to do is talk you through the next step, which is creating the Conda environment based on the configuration files in this repository. And once I get that started, that's going to take a little bit, I'll come back and I'll discuss in detail kind of the structure of this project template, as well as the details of the software stack that has been included in the Conda environment file. Okay. So the Conda environment file, of course, defines all of the channels and the dependencies that you would like to include in the project. So we're going to build a Conda environment from this file. Now, I've included two kind of convenient scripts. So one is this create Conda environment shell script, which will use Conda to create an environment based on the configuration files in the project root directory. That's the environment.yaml and the requirements.txt. You could run this script on the login node and build your environment. However, my experience is that building Conda environments on the login node is both slow, because the login nodes on Ibex are typically heavily used by other users, and also prone to disruption. So if you're connected via Wi-Fi and you happen to lose your connection to Ibex, to those login nodes, your Conda environment creation could get canceled in the middle of creating the environment, and you'll have to start all over again, and it can just be a little troublesome. So what I have found is both faster and more robust is to actually use Slurm to submit your Conda environment creation script as a job on the cluster. So I've created a second script, which does exactly that. So this just wraps the shell script, but then adds some Slurm headers to launch the Conda environment creation as a job on the partition, the debug partition, ask for a couple of cores, about 8 gigs of memory, and 2 hours. And it won't take 2 hours, but that's kind of the maximum time that's allowed in debug partition, I think, at this point. So we can use this script to launch our job. So let's go ahead and do that. So sbatch bin create Conda environment sbatch. And we can hit enter, and there's our job. And you can check just to make sure that that job is running. And it is indeed already running. And so we'll just let this run for a while. And then we'll come back and check on it. Okay. Okay, so now while the Conda environment is being created for us, I want to talk a little bit about both the structure of this template repo and then also the Conda environment itself. So I based the structure of this template repo off of a paper called Good Enough Practices for Scientific Computing. There's a link to the paper. It's a great little paper. It'll help you think through some ideas of how you should organize your projects. And so I've tried to kind of take those suggested best practices and kind of encode them in this template repo for you. So in particular, there's kind of 10 rules here that I've embedded in this template repo. So the first is that every new project should have its own project directory. So the project directory is basically the directory you get when you clone this repo. So you would clone this repo for a new Scikit-Learn project. So that's what we're doing. So put your external scripts or your compiled programs in the bin directory. So I typically don't have any compiled executables because I tend to not be compiling my own code. So in the bin directory, I typically have these Conda environment creation scripts, but then also my job submission scripts for when I'm submitting jobs via Slurm to Ibex. I'll put those scripts in this bin directory. Okay. So next, put your data on metadata in the data directory. So I have a placeholder data directory here. So I tend to put all my raw data files in my data directory. So this would live on Scratch because the project directory itself is on Scratch. If your data is already in some other directory on Scratch and it's rather large, you can put a symlink in this directory to link that other data directory to this data directory. So your scripts and your notebooks can still reference the data directory inside your project. So that's another good. And maybe I'll make a little video on how to do that later. There is a doc directory. So this is where you would put any kind of documentation or drafts of papers that you might be writing based on your project. I would put those in the doc directory. I have a Docker directory, which you can use if you want to run this project on your local laptop, your workstation where you have Docker installed. Then you can use Docker within your development cycle. Maybe I'll make a separate video on that as well. I don't want to get into the contents of this directory now. I have a notebooks directory. So the notebooks directory is where I would keep all my Jupyter notebooks. Basically, I use Jupyter notebooks and Jupyter Lab almost exclusively when developing my data science machine learning projects. So I'll keep my notebooks in a directory separate from my Python scripts. Speaking of Python scripts, I tend to keep those in my source directory. So this is a placeholder directory. All my script that I would use for my training jobs on Ibex will be kept in my source directory, separate from my notebooks, which I use more for prototyping. Right, and then results. Any results like images or other statistical results or things like that that I want to keep. I will put those in the results directory just to keep everything kind of separate, neat, tidy. My Slurm output and error files from my jobs that I submit to Ibex, I tend to also put those in separate folders within the results directory. Okay, so that's a little bit of a discussion on what is in the structure of this template repo. So let's go back and check on our environment creation job. So if we look back at the SBatch, so the SBatch has the slurm output and error files actually going to the bin directory. So inside the bin directory, there should be some create conda slurm out and slurm error script. So let's look at the slurm error script. So that was listing the slurm error script. So let's look in the slurm error script. So there's nothing there. And now let's look at the out. Okay, so the slurm.out shows that there are packages that are being downloaded and extracted. So we're kind of in the first phase of the Conda environment creation. So you can see here that Conda has collected all the metadata on the packages that you want to install. It has started solving the environment, and it managed to do that. And now it's downloading, extracting whatever packages it needs. So progress is being made, and we'll come back to that momentarily. Okay, so let's go back and talk about the environment file itself. Okay, so what I've done is now I'll walk through basically the contents of this environment file and talk about some of the packages that I have installed here. So the first thing that I want to call your attention to is the channels. So in addition to the Conda Forge and the defaults channel, which are two channels that are included in every Conda environment that I create, and if you've come along to any Conda training that we've provided at KVL over the past several semesters, then you will be familiar with Conda Forge and the defaults channel because they feature heavily in those trainings. The new channel here is the Intel channel. So Intel is a heavy user of Conda. They're a big advocate for using Conda to manage software stacks. And they have made their own Conda channel. And through that channel, they distribute precompiled binaries for very common data science, machine learning, deep learning packages that are specifically optimized for Intel CPUs. So we can add the Intel channel as the highest priority channel. And then what we'll find is that a large number of these packages that are maintained by Intel will be installed. And so we'll automatically get these optimized for Intel CPU versions of these various packages. Now, not all of them are included in the Intel channel. Some and those that aren't included in the Intel channel get picked up by Conda Forge, but many of them, including the ones that are most performance critical, will be picked up from the Intel channel. Now, one of the things that you need to do is at the time of this, that I'm making this video, Intel uses Python 3.7 for all of their builds. So you do need to peg the Python version to be 3.7 in order to make sure that Conda finds builds in the Intel channel for these packages. If you put 3.8 or 3.9, then you won't find these packages in the Intel channel, and you'll end up getting everything from Conda Forge, which is not what you want. So at least for the moment, Python 3.7 is what Intel uses. Okay, so let's go through these packages. So the first package that I am including is Bokeh. So Bokeh is a library for doing interactive data visualization. And so I have included that in the environment. So Dask is a library for scaling your kind of NumPy, Pandas, and Scikit-Learn based workflows across multiple nodes in a cluster seamlessly. So that has been included in the environment. Also, Dask ML, which is a add-on to Dask that provides a number of different algorithms and routines for accelerating and scaling out your machine learning workloads on Dask, complements algorithms found in Scikit-Learn and other packages. And then there's a nice extension for Jupyter Lab called the Dask Lab extension that allows you to monitor the progress of your Dask jobs on the cluster on which they're running from within Jupyter Lab. And so I've included that as well, and as well as Jupyter Lab, which I'll talk about in a minute. Kind of going through these in alphabetical order. So Data Shader is another very large-scale plotting tool that I have included. If you have large data files that you wish to plot or you need to plot, then you can plot them with Data Shader. So it's included. I've included Feature Tools, which is an algorithm for feature engineering, or it's not an algorithm, is a library or a package for performing feature engineering. It has a number of kind of convenience tools for generating different combinations of features for different applications, including classification and regression problems. It has nice tools for building out features for time series prediction. So very handy. Another visualization package is HoloViews. So HoloViews is also within the Bokeh ecosystem, is kind of a higher level API on top of Bokeh's more lower level API for plotting and doing interactive visualization. I've included HVPlot, which is provides pandas bindings for HoloViews. So if you're using pandas and you like to use the .plot method to plot your data frames, by default, when you call the .plot method on a data frame, it's going to use matplotlib, but it can use different backends for visualization, including HoloViews, but you need the HVPlot library in order to do that. So I've installed the HVPlot library as well. Next is Imbalance Learn. So Imbalance Learn is kind of a toolkit for helping you solve classification problems where your training data set is very imbalanced, where you have large numbers of only a small number of classes and then small numbers of training samples for other classes that you need to predict. Imbalance Learn can help you with some of the improve the performance of your classification algorithm by providing you with some sampling techniques and other strategies to deal with imbalanced classes. So I've included that. Jupyter, so obviously we're going to need Jupyter Notebooks and Jupyter Lab in order to use that as the primary interface through which we will do our development and our prototyping work for our machine learning and data science workflows on Ibex. I'll have a follow-on video on how to launch your Jupyter Lab or Jupyter Notebook servers on top of Ibex. So watch out for that. It should land shortly. So a couple other Jupyter Lab plugins. So Jupyter Lab Git, so that you can interact with Git and GitHub when you're doing your development, your prototyping work. I like to have my GitHub repositories, linked to Ibex, so that when I'm doing work, I can version control everything, so that all of my code and job scripts and things like that are all being version controlled and stored on GitHub. So Jupyter Lab Git allows you to do that from within Jupyter Lab whilst you're running on Ibex. Jupyter Lab Language Server Protocol. So this gives you a lot of nice IDE features in your Jupyter Notebooks and IPython consoles and Python scripts, hovering, diagnostics, definitions, auto-completion, hinting, things that you would expect from an IDE. You can get them, but you have to, you can get them in Jupyter Lab, but you need this Jupyter Lab extension to accommodate that. Okay, so LightGBM. So this is a gradient boosting machine framework. Very popular, widely used on Kaggle. Is very fast, very scalable. And works on CPUs and GPUs, but this would be the CPU implementation. So that is installed in the package as well. Matplotlib, kind of the default plotting library in Python, so that's been installed. Numba. So Numba is a really cool package that you should be aware of. So it's a just-in-time compiler for Python, so you can write like straightforward Python functions and then JIT compile them so that they will run at C++ compiled speed. And unless you are an expert C or C++ programmer, the JIT compiled versions of your Python functions will likely run faster than what you would get if you tried to hand code the functions in C or C++ yourself, unless you're very, very good at C or C++. This has been my experience. So in addition to numba, of course, we have numpy. It's kind of the standard n-dimensional array computing library in Python. So I've installed Optuna. So Optuna is a toolkit for doing hyperparameter optimization. So it's a very, very important step in optimizing your machine learning and data science pipelines. Optuna can work with many libraries, as you can see here: PyTorch, Chainer, TensorFlow, Keras, MXNet, what have you. I'm installing it here so that you can use Optuna to do hyperparameter optimization for your Scikit-Learn projects. Pandas, of course, Pandas is the standard library for doing data analysis in Python, so we need that. Panel, so Panel is a great library that builds on the bokeh, HoloViews, hvplot data shader ecosystem to provide kind of high-level dashboarding, so you can create web apps and dashboards for your application. So I've included that. Pip, this is kind of here as a public service announcement. So it's very important for you to install pip in every Python environment that you build with Conda. You're going to need pip to install things that aren't available via Conda. It's very, very important that the pip that you use to install is a pip that's installed inside your Conda environment. That way you can be sure that your pip installed packages end up inside your Conda environment, not somewhere else in your home directory or somewhere else entirely. And it can avoid a lot of difficult to debug and support issues that I see come up a lot with Ibex users who are trying to use Conda and pip and not doing it properly. Okay, so Apache Arrow. So Arrow is a kind of a consistent in-memory data storage format that allows you to access your data from within a number of analytics engines, including Pandas, as well as a number of on-disk storage options. So it avoids a lot of these kind of like copy and conversion steps that you need if you have to move from different on-disk storages to different analytics engines. You can replace all of those with Arrow. And it's a good way to think about storing your data in memory. So once your data is in memory, then it's much faster to access. So one of the common issues we see with Ibex users and trying to get performance is that all their training data ends up being on disk and they're constantly reading from disk. Much better to get your data into memory using something like Apache Arrow and then read the data directly from CPU memory when you're doing your training. It'll be much, much faster. Python language server. So this is basically, this goes hand in hand with the Jupyter Lab language server protocol to provide those nice IDE-like behavior. PyViz comms. So this is the library that provides the Jupyter Lab widgets and extensions for HoloViews and data shader and hvplot and things like that. Next, we have Scikit-Learn. Of course, we're going to have Scikit-Learn in the Scikit-Learn project. Then we have SciPy. So SciPy is the, I think of it as like the adding the MATLAB-like toolboxes that you get on top of NumPy. So you add SciPy when you need to have optimization and signal processing and other things like that. What's next? So shape. The shape or SHAP for Shapley or Shapely values. So this is a library that helps you understand what is causing or what is generating the predictions of your machine learning model. So it's a way that's based on some ideas from game theory using something called Shapely values that allows you to get a better understanding of what features are driving the predictions of your model. So very important if you want to try to understand like what is going on, why is your model predicting what it's predicting. Dimensionality reduction algorithm that's become very popular, UMAP. It's a nice scalable algorithm that is similar to Tisney, which has been around for a little bit longer and is perhaps more widely known. So I'm adding it here. Weights and biases. Not quite sure why I'm being taken to the sign up page. Let's do it this way. Weights and biases AIs. This is what I want. Nope. There we go. Okay. So weights and biases. So weights and biases is an API for managing your machine learning experiments. So it's never just like one set of hyperparameters or one set of training data or things like that you typically use. You're typically doing a lot of different experimentation and prototyping with machine learning workflows. And when you start doing all these experiments, you need a way to manage them. So weights and biases is a popular API and tool for managing your experiments. Has a fairly large number of users that counts who have been using weights and biases and are very happy with it. So I'm adding it here. You do need to sign up for an account, and an account is free, and I think they have different tiered plans. But with a free plan, you can get probably most of what you need to get done. So that's already pre-installed. So Xarray, Xarray basically tries to take the ideas of NumPy with n-dimensional arrays, but with the nice indexing of pandas and combine the two together. So this is a very powerful tool for anybody who is working with who wants to do machine learning on input data that consists of large numbers of potentially very large netCDF files. The Xarray and Dask combination is very, very powerful. They work very well together. If you are doing, weather and climate data analysis, and you want to do machine learning on that data, you need to have Xarray in your environment. Zeus Python is an alternative. Is a Jupyter kernel for Python that has some nice additional features and some better performance than the default Jupyter kernel for Python that you get in Jupyter Lab. I've installed that. You can look through the documentation and see kind of some of the other benefits that you get from Zeus Python. And finally, XGBoost. So XGBoost is my go-to machine learning algorithm to set a benchmark for any new project that I do. I always start with XGBoost. Wins the most Kaggle competitions, widely used throughout industry, in part because it scales very well, not just on a single node, but across multiple nodes, on CPUs and GPUs. Can't recommend it enough. It's installed here. There are various gradient boosting algorithms in Scikit-Learn proper, but their implementations do not tend to scale as well as XGBoost. So start with the implementations in Scikit-Learn, get an idea of how that works, and then once you know that you definitely want to use XGBoost or a gradient boosted machine, then take a look at either LightGBM or XGBoost. They integrate very well with the Scikit-Learn pipelines, and so I've included that basically in the environment as well. Okay, so that's gone through everything that is defined in the environment. So I went through all of these packages. So now let's go back and see what is going on. So I'm just going to up and take a look at that. Oh, looks like we're done. So that didn't take too terribly long. Oh, there we go. Okay, so we can see. Let's just look here and see what happened. So we had all of these downloads. So a lot of MKL downloads. That's because we're using a lot of these libraries are from the Intel channel. So you're going to get a lot of Intel's low-level linear algebra libraries that are optimized and targeting Intel hardware. So you can see a lot of MKL packages in here, as well as TBB, which is threaded building blocks for Pi, as well as TBB threaded building blocks as well will be installed. That's there. What else? So there is some DAL for Pi. So DAL is a package to accelerate Intel CPU-based machine learning algorithms. It combines kind of with Scikit-Learn. In fact, you have a little message here that Intel has put inside of the Conda packages, telling you that you have installed Scikit-Learn that can be accelerated with DAL for Pi. And if you want to use DAL for Pi, then you need to set this environment variable in your script. This would be in your job script when using it. So I guess I'll have to make a video showing you how to do that. And then we have the pip dependencies. So there's only this single pip dependency that gets installed, and all of these other dependencies are already added in the Conda environment itself, so it didn't need to install any things for that. I guess I didn't mention this dependency. So this pandas bokeh package is basically the pandas bindings for bokeh. So if you want to use bokeh as a plotting backend for your plotting data from your pandas data frames, then you need this package. So I've installed that. And then, so we should be able to activate our environment. So let's try to do that. So if we do conda activate /env, and then if we do a conda list, yeah, you can see all of the packages. So you'll recognize many of the names of packages that I just went through: XGBoost, Zeus Python, Xarray, and then all these other packages whose names I didn't go over are the dependencies or the dependencies of dependencies and so forth that you need for these packages. And over here on the channels, you can see that many of these packages are coming from Intel. So XGBoost came from Intel. Where is another? Let's go find Scikit-Learn. So SciPy, Scikit-Learn came from Intel. Let's look at it. Look for pandas. So pandas came from Intel. NumPy and NumPy came from Intel. And then, of course, we get all of these MKL libraries, Intel's math kernel libraries from Intel, and so on. So I think Dask. So here's Intel Python, Intel OpenMP, and Dask, I think. No, Dask is coming from CondaForge. Okay. So then, and then we have DAL. So these are the DAL for Pi. These are the libraries that are being used to accelerate Scikit-Learn if you enable them. Okay, cool. So I think that's pretty much everything that I wanted to include in this video. It was just supposed to show you how to kind of use this template repo, clone it down onto Ibex, build the Conda environment, and then kind of walking you through kind of what's available and what's there. So in follow-on videos, I will, I'll add some things like launching a Jupyter notebook, a Jupyter Lab server on Ibex using this environment. I'll add some job scripts, some examples of launching Scikit-Learn based jobs on Ibex, maybe some examples of how to do hyperparameter tuning for your Scikit-Learn based jobs on Ibex. I don't know, anything that I can think of that might add some value, make it a little easier for you to get started. If you have your own things that you would like to include on this channel, or to get some extra help, please leave a message in the comments or contact us on Slack or via email and give us some ideas, and maybe we can make some videos on any topics you might have. Okay, so good luck with Scikit-Learn on Ibex.